In geometry, the circumscribed circle or circumcircle of a polygon is a circle which passes through all the vertices of the polygon. The center of this circle is called the circumcenter and its radius is called the circumradius. A polygon which has a circumscribed circle is called a cyclic polygon. All regular simple polygons, isosceles trapezoids, all triangles and all rectangles are cyclic. A related notion is the one of a minimum bounding circle, which is the smallest circle that completely contains the polygon within it. Not every polygon has a circumscribed circle, as the vertices of a polygon do not need to all lie on a circle. But every polygon has a unique minimum bounding circle, which may be constructed by a linear time algorithm. Even if a polygon has a circumscribed circle, it may not coincide with its minimum bounding circle. For example, for an obtuse triangle, the minimum bounding circle has the longest side as diameter and does not pass through the opposite vertex. Triangles. All triangles are cyclic, i.e., every triangle has a circumscribed circle. This can be proven on the grounds that the general equation for a circle with center and radius are in the Cartesian coordinate system is since this equation has three parameters, only 3 points coordinate pairs are required to determine the equation of a circle. Since a triangle is defined by its three vertices, and exactly 3 points are required to determine a circle, every triangle can be circumscribed. Straight edge and compass construction. The circumcenter of a triangle can be constructed by drawing any two of the three perpendicular bisectors. The center is the point where the perpendicular bisectors intersect, and the radius is the length to any of the three vertices. This is because the circumcenter is equidistant from any pair of the triangle's vertices, and all points on the perpendicular bisectors are equidistant from two of the vertices of the triangle. Alternate construction. And alternate method to determine the circumcenter is to draw any two lines, each one departing from one of the vertices at an angle with the common side. The common angle of departure being 90 degrees minus the angle of the opposite vertex. In coastal navigation, a triangle's circumcircle is sometimes used as a way of obtaining a position line using a sextant when no compass is available. The horizontal angle between two landmarks defines the circumcircle upon which the observer lies. Circumcircle equations. Cartesian coordinates in the Euclidean plane. It is possible to give explicitly an equation of the circumcircle in terms of the Cartesian coordinates of the vertices of the inscribed triangle. Suppose that are the coordinates of points A, B, and C. The circumcircle is then the locus of points V equals in the Cartesian plane, satisfying the equations guaranteeing that the points A, B, C, and V are all the same distance r from the common center U of the circle. Using the polarization identity, these equations reduce to the condition that the matrix has a non-zero kernel. Thus, the circumcircle may alternatively be described as the locus of zeros of the determinant of this matrix. Using cofactor expansion, let we then have A, V, 2 minus 2 subverts minus B equals 0 and, assuming the 3 points were not in a line, V minus S, A, 2 equals B, A plus, S, 2, A 2, giving the circumcenter S, A and the circumradius square root. A similar approach allows one to deduce the equation of the circumsphere of a tetrahedron. Parametric equation. A unit vector perpendicular to the plane containing the circle is given by hence, given the radius, r, center, pc, a point on a circle, p0 and a unit normal of the plane containing the circle. One parametric equation of the circle starting from the point p0 and proceeding in a positively oriented sense about is the following. Trilinear and barycentric coordinates. An equation for the circumcircle in trilinear coordinates x, y, z is a, x plus b, y plus c, z equals 0. An equation for the circumcircle in barycentric coordinates x, y, z is a2, x plus b2, y plus c2, z equals 0. The isogonal conjugate of the circumcircle is the line at infinity. given in trilinear coordinates by x plus by plus c z equals 0 and in barycentric coordinates by x plus y plus z equals 0. Higher dimensions. Additionally, the circumcircle of a triangle embedded in d dimensions can be found using a generalized method. Let A, B, and C be d-dimensional points, which form the vertices of a triangle. We start by transposing the system to place C at the origin. The circumradius, r, is then where theta is the interior angle between A and B. The circumcenter, P0, is given by this formula only works in 3 dimensions as the cross product is not defined in other dimensions, but it can be generalized to the other dimensions by replacing the cross products with following identities. Circumcenter coordinates. Cartesian coordinates. The Cartesian coordinates of the circumcenter are without loss of generality. This can be expressed in a simplified form after translation of the vertex A to the origin of the Cartesian coordinate systems, i.e., when A equals A minus A equals. In this case, the coordinates of the vertices B equals B minus A and C equals C minus A represent the vectors from vertex A to these vertices. Observe that this trivial translation is possible for all triangles, and the circumcenter coordinates of the triangle ABC follow as with trilinear coordinates. The circumcenter has trilinear coordinates cos alpha, cos beta, cos gamma, where alpha, beta, gamma are the angles of the triangle. In terms of the side lengths A, B, C, the trilinears are barycentric coordinates. The circumcenter has barycentric coordinates where A, B, C are edge lengths of the triangle. In terms of the triangle's angles, the barycentric coordinates of the circumcenter are circumcenter vector, since the Cartesian coordinates of any point are a weighted average of those of the vertices, with the weights being the point's barycentric coordinates normalized to sum to unity. The circumcenter vector can be written as here: U is the vector of the circumcenter and A, B, C are the vertex vectors. The divisor here equals 16s2, where S is the area of the triangle. Cartesian coordinates from cross and dot products in Euclidean space. There is a unique circle passing through any given 3 non-collinear points P1, P2, and P3. Using Cartesian coordinates to represent these points as spatial vectors, it is possible to use the dot product and cross product to calculate the radius and center of the circle. Let then the radius of the circle is given by the center of the circle is given by the linear combination where location relative to the triangle. The circumcenter's position depends on the type of triangle. If and only if a triangle is acute, the circumcenter lies inside the triangle. If and only if it is obtuse, the circumcenter lies outside the triangle. If and only if it is a right triangle, the circumcenter lies at the center of the hypotenuse. This is one form of Thales' theorem. The circumcenter of an acute triangle is inside the triangle. The circumcenter of a right triangle is at the center of the hypotenuse. The circumcenter of an obtuse triangle is outside the triangle. These locational features can be seen by considering the trilinear or barycentric coordinates given above for the circumcenter. All 3 coordinates are positive for any interior point, at least one coordinate is negative for any exterior point, and one coordinate is 0 and 2 are positive for a non-vertex point on a side of the triangle. Angles. The angles which the circumscribed circle forms with the sides of the triangle coincide with angles at which sides meet each other. The side opposite angle alpha meets the circle twice, once at each end, in each case at angle alpha. The alternate segment theorem states that the angle between the tangent and chord equals the angle in the alternate segment. Triangle centers on the circumcircle of triangle ABC. In this section, the vertex angles are labeled A, B, C, and all coordinates are trilinear coordinates. Steiner point equals BC. California. AB equals the non-vertex point of intersection of the circumcircle with the Steiner ellipse. is the ellipse of least area that passes through A, B, and C. An equation for this ellipse is 1 plus 1 plus 1 equals 0. Tarry point equals sec. Sec equals antipode of the Steiner point. Focus of the Kuiper parabola equals CSC. Other properties: the diameter of the circumcircle, called the circumdiameter and equal to twice the circumradius, can be computed as the length of any side of the triangle, divided by the sine of the opposite angle. The triangle's 9-point circle has half the diameter of the circumcircle. The diameter of the circumcircle of the triangle delta ABC is where A, B, C are the lengths of the sides of the triangle and S equals 2 is the semi-perimeter. The expression above is the area of the triangle, by Heron's formula. Trigonometric expressions for the diameter of the circumcircle include in any given triangle. The circumcenter is always collinear with the centroid and orthocenter. The line that passes through all of them is known as the Euler line. The isogonal conjugate of the circumcenter is the orthocenter. The useful minimum bounding circle of 3 points is defined either by the circumcircle or by the 2 points of the longest side of the triangle. It is common to confuse the minimum bounding circle with the circumcircle. The circumcircle of 3 collinear points is the line on which the 3 points lie, often referred to as a circle of infinite radius. Nearly collinear points often lead to numerical instability in computation of the circumcircle. Circumcircles of triangles have an intimate relationship with the Delaunay triangulation of a set of points. By Euler's theorem in geometry, the distance between the circumcenter O and the incenter I is where R is the incircle radius and R is the circumcircle radius. Hence the circumradius is at least twice the inradius, with equality only in the equilateral case. The distance between O and the orthocenter H is for centroid G and 9-point center N. We have the product of the incircle radius and the circumcircle radius of a triangle with sides A, B, and C is with circumradius R, sides A, B, C, and medians MA, MB, and MC. We have if median M, altitude H, and internal bisector T all emanate from the same vertex of a triangle with circumradius R. Then Carnot's theorem states that the sum of the distances from the circumcenter to the 3 sides equals the sum of the circumradius and the inradius. Here a segment's length is considered to be negative if and only if the segment lies entirely outside the triangle. If a triangle has 2 particular circles as its circumcircle and incircle, there exist an infinite number of other triangles with the same circumcircle and incircle, with any point on the circumcircle as a vertex. A necessary and sufficient condition for such triangles to exist is the above equality cyclic quadrilaterals. Quadrilaterals that can be circumscribed have particular properties, including the fact that opposite angles are supplementary angles. Cyclic n-gons. For a cyclic polygon with an odd number of sides, all angles are equal if and only if the polygon is regular. A cyclic polygon with an even number of sides has all angles equal if and only if the alternate sides are equal. A cyclic pentagon with rational sides and area is known as a Robbins pentagon. In all known cases, its diagonals also have rational lengths. In any cyclic n-gon with even n, the sum of one set of alternate angles equals the sum of the other set of alternate angles. This can be proven by induction from the n equals 4 case. In each case replacing a side with 3 more sides and noting that these 3 new sides together with the old side form a quadrilateral which itself has this property. The alternate angles of the latter quadrilateral represent the additions to the alternate angle sums of the previous n-gon. Let one n-gon be inscribed in a circle, and let another n-gon be tangential to that circle, at the vertices of the first n-gon. Then from any point P on the circle, the product of the perpendicular distances from P to the sides of the first n-gon equals the product of the perpendicular distances from P to the sides of the second n-gon. point on the circumcircle letter cyclic n have vertices a1, and on the unit circle. Then for any point m on the minor arc a1 and the distances from M to the vertices satisfy polygon circumscribing constant. Any regular polygon is cyclic. Consider a unit circle, then circumscribe a regular triangle such that each side touches the circle. Circumscribe a circle, then circumscribe a square. Again circumscribe a circle, then circumscribe a regular five-gon, and so on. The radii of the circumscribed circles converge to the so-called polygon circumscribing constant. The reciprocal of this constant is the Kepler-Beauchamp constant.